In this video, we'll show how MATLAB can be used to perform Laplace transforms using the symbolic math toolbox and the commands Laplace and iLaplace. We'll consider one of the example functions that we've looked at already. First, we need to define symbolic variables. I'll define the symbolic variable t and a function of time f of t, telling MATLAB that these are symbolic variables. Then I'll tell MATLAB that f is t times e to the minus t. Next, I'll assign the Laplace transform of little f of t to the variable capital F. MATLAB correctly finds the Laplace transform of little f of t. We can also use the iLaplace function to take the inverse Laplace transform of f. And MATLAB converts it back to the time domain, assuming that t is the independent variable. We can also use the Laplace transforms to solve ordinary differential equations. Let's again define a symbolic variable t, and this time a function y of t. We also need a variable representing the derivative of y. I'll call it dy dt, and I'll tell MATLAB that this is the derivative of y with respect to t. We can use the diff command to define higher order derivatives as well. Next, we'll write a differential equation that we used in one of the previous videos and take its Laplace transform. Don't forget that when writing equations, you need to use the double equal sign. The equal sign in MATLAB is the assignment operator, and the double equal sign is the equal sign. We'll give this a name. We'll call it ODE. Now you need to know something about how MATLAB displays the Laplace transform. We would call this capital Y of S, but MATLAB is much more explicit. It says that this is the Laplace transform of y of t, assuming that t is the independent variable in the time domain and s is the independent variable in the Laplace domain. Similarly, this is also capital Y of S. So you and I might write this equation using capital Y of S for Laplace yts. You can compare this to the example that we did earlier to confirm that indeed this is the Laplace transform of this ODE. When using the symbolic math toolbox in MATLAB to take Laplace transforms, we should be very careful about assigning constant parameters. Suppose we have the symbolic variables t, y1 of t, and a, where a we want to be a constant. We could take the Laplace transform of y1, and MATLAB tells us that it knows what the Laplace transform of y1 is. What happens if we take the Laplace transform of the constant? You remember that the Laplace transform of the constant should be a over s. Now, why did it do that? Well, our quantity a here that we're taking the Laplace transform of is not a function of time. And MATLAB's trying to be clever here and figures that we want to take the Laplace transform of a, where a is the time domain independent variable, because it didn't see a t. It looked for the next variable it could find and assumed that a was equal to the time domain independent variable, when in fact we want a to be a constant. So instead, we should explicitly define a, t, and s, and then ask MATLAB to give us the Laplace transform of a, assuming that the independent variable in the time domain is t, and the independent variable in the Laplace domain is s. And now MATLAB correctly understands that a is a constant, and it gives us the answer a over s. If there's a t appearing anywhere in your expression that you take the Laplace transform of, MATLAB will assume that that t is the time domain independent variable. But if t is missing, it will choose another variable. Similarly, MATLAB will look for an s in a Laplace domain function when taking the inverse Laplace transform and assume that s is the Laplace domain independent variable. But if it can't find an s, it'll assume that some other variable is the Laplace domain independent variable. By providing two additional input arguments to the Laplace function, we can tell MATLAB explicitly which variable we want to be the independent variable in the time domain and which variable we want to be the independent variable in the Laplace domain. This way, MATLAB doesn't have to guess what we want. MATLAB can also be used to take some fantastic shortcuts so that you don't have to do partial fraction expansions, for example. Let's revisit the problem that we did on slide 311. On slide 311, we arrived at a function of s that had a fourth order polynomial of s in the denominator. And to invert this back to the time domain, we had to do a partial fraction expansion to find 4 coefficients. MATLAB can do all of this for us in a single step. If you compare this solution to the solution on slide 311, you'll see that MATLAB correctly found the inverse Laplace transform. MATLAB, of course, also has no problem handling the types of things that make things more complicated for us when doing it by hand. For example, complex roots or repeated roots. This was our example from slide 315 that had complex roots of the denominator polynomial. And you can see MATLAB gives us the correct exponentially decaying sine function.